right, so thank you for joining a live stream of today's lab. Okay, so lab, today we're going to figure out the molecular mass of two gases. One is helium, one is argon, okay? And to do so, hey, we're using our molecular mass, fancy M, pinky up, is equal to dirt over P. Now, we're going to split this dirt up into grams per volume, okay? So, party people, the first thing is to notice what flask we're using, okay? And the flasks have a certain volume. What we're going to skip in this this stream is that someone previously has taken this plastic Erlenmeyer flask, filled it up with water, okay? Well, my blue marker's being present, so sort of. They filled it up with water. Okay, it's green, but hey, maybe there's algae in it. In any case, they filled it up with water to the tippy top, and they poured it into a graduated cylinder, and they measured the volume of that space. The space of the water is the space the gas would fly in, and we have those values up there depending upon what flask you pick. So we have the volume. Okay, the grams, of course, we're going to get by taking our flask, okay, which we're going to put a cap on it, and we're going to measure it on a graduated cylinder. Okay, and of course it's going to have air in it. Okay, all right. Now you're going to measure that on a scale and measure the volume of your flask and the air. To get the measurement of just the flask evacuated, we know the density is equal to 1.17 grams per volume per liter. Sorry, the volume liter is the volume. And so what we're going to do is whatever your volume is of your flask, I'm going to give that to you because another set of students have done that already. Okay. In liters, we know solving for density equals mass over volume. We know that mass is equal to density times volume. So we're going to take our density, 1.17 grams, times it by our volume, grams per liter, forgot that unit there, and then times it by the liter. Okay, remember I convert that to liters. That'll give us the grams of air, okay, in the flask. That's an important value. We're going to subtract that from the mass of the air and the container to get our empty container. That's the important part, because we need an evacuated container. That's the important part. So once we know the mass of just the container without the air by subtracting the mass that we get by using the density of air, now we're going to take this and flush this with the two gases in the container I'm going to show you with. And then we're going to put it on, stopper them, put them on, subtract out the container, and we're going to get the grams of the two gases. The volume of our two gases are whatever containers we pick, okay, that students have already filled up with water. The key here is what's the temperature today? The temperature today inside the classroom is 20.5 degrees Celsius. You know that has to go into an absolute scale. The pressure today takes a little bit of calculation. The pressure, I do not have a barometer, which is a closed-end manometer in the classroom. So I go to the local weather station here for West Hampton Beach, and I got a barometric pressure of 30.15. So there's 30.15 inches of mercury. Now we should know what this means. Okay? You've got some kind of open tube possibly. And we have mercury, which is not black, by the way. This is a closed-end tube. Okay? And so this open tube of air hits the surface and supports this height in inches of mercury. Why are they using inches? Because this dumb English system is still holding true. All right? So height of inches of mercury has been measured to be 30.15. Okay? There's no opposing pressure here. This is a vacuum. Mercury doesn't evaporate very well. So the only pressure the force over area being supported is the height of the mercury. But we've got to convert that into a pressure unit because we have R. If we're going to use 0.0821 atmospheres liter mole kelvins, hello, we've got to be in atmospheres. So how do we do that? Pretty simple stuff. Using our conversions. Okay, take my inches of mercury, get rid of an inch. We're going to use our units here. For every 1 inch, if you don't know this, you could look it up. There's 2.54 centimeters. Well, we want to convert this to millimeters. Well, I'll just do this first. You can combine it. Okay? And then I want to get rid of centimeters. I know that a centimeter is 10 times bigger than a millimeter, but I want to go into millimeters of mercury. That's a pressure unit. That's a torr. Okay? That's something we know of as a standard. So every 1 centimeter is 10 millimeters. Notice I'm using my unit so fun here. Okay? And then I'm left with, okay, millimeters of mercury. Millimeters of mercury is a pressure unit, and there's a standard amount that Torricelli found. So, what am I going to do? I'm going to cancel out millimeters of mercury. And what do I know? At sea level, standard pressure is 760 millimeters of mercury. What's the standard pressure for atmospheres? Hey, that's 1. So I'm converting it to atmospheres because I want to be in the unit that my gas law is using. Now, if I'm using the gas law constant in torr, I could keep that as 760 millimeters of mercury, which is a torr. Cancel your units away. And you're left with atmospheres. Okay? So let's go find that value. Okay? And my calculator looks like I left it somewhere else. So someone calculate that for me. Oh, it's not right here. Okay. And that'll be our pressure in atmosphere today. So P is equal to whatever that is in atmospheres. I think that's going to be a little bit greater than 1. What'd you get?
Yeah, 1.008.
1.008 atmospheres. That sounds right. Okay? And that's your pressure today. Convert that to Kelvin. You have everything, there's your pressure. All we need to do to figure out our molecular mass is find the mass of our 2 gases. Okay, so we're going to move to the tables in the back. Okay, so come with me. $92.859 we can use. Yep.
What is it? 98 what?
859. Okay. Now what you can do now, volume of D is 516 milliliters. Somebody filled this up with water to the tippy top, measured it with a graduated cylinder, and found that this flask has 516 milliliters. What's that in liters? 0.516 liters. Okay. Now, what you're going to have to do now is calculate the mass of the air in the flask. So knowing the density of air is 1.17 grams per liter, and now that you know that the volume for this container by the other lab students filling this up, you know this to be 0.516. Forget that density triangle, people. Okay? This is D, by the way. So density is equal to the mass times the volume. I'm sorry. The mass is equal to density times volume. Find that mass. Okay. Subtract the mass of the air by using the density from the mass of our air end. So subtract the air mass that's in this container from the mass of the air and the container, and now you have the mass of a what? Dry, evacuated container. Kind of cool that we can do it without, because it's very difficult to take all the air out, because it wants to seep back in because of entropy. So take the air that you get by taking 1.17 grams per liter and timesing it in this case by 0.516 liters, and you've got the mass of this air. Subtract it from this number of 92.859, and now you have the mass of the dry container, cool beans. Now we're going to take this container over and we're going to do our first gas. Now this gas, okay, is lighter than air. Okay, so student E, why don't you come over?
You gonna trust me?
No, but we're going to have to. Okay, so grab it. Okay, take the top off. Show the fans at home taking the top off.
Yeah.
Good.
Yep.
Now, what you have is a balloon valve here. Notice it's turned upside down because this gas is lighter than air. So all you got to do is bend it and the air comes out. So invert your flask.
Yeah.
And what you're going to do is flush out, okay, the air. So bend it. Make sure that your container stays straight up. Because if you do it the other way, the gas is going to empty. So it's filling. Be aggressive. Come on. Good. And that is student E's gas. Come on, do some more. Good, stop. Now leave it. Where is your top? Someone grab it, okay. Now, do not turn that flask over. If you do, the gas will be all gone.
Okay.
Now, so screw it on. Don't turn it upside down yet, right side up yet. Nice and tight. Oh, you can do this. Keep it right side up. Upside down. Because that gas is so light, it'll tighter. Be aggressive.
It's tight.
Good. Let's go back to the scale. And now let's measure it again. Oh, let's wait till it zeros. Wait till it zeros. Don't be aggressive. Okay. So now you get 92.295. Subtract out the mass of the container. The mass of the container is the container minus the density of the air, right? So subtract out the mass of the evacuated container you just found by subtracting out the density of air from the air in the container, and now you have the mass of gas A. Okay. All you need to do now to find the molecular mass of gas A, okay, is take the what? The grams, put that mass there, times it by the R, the temperature, the V, and the P. But before we do any of that, let's grab this flask. Okay. Okay, now all I want you to do here is unscrew the top.
Like with it upside?
Yep, because I want the helium gone. That was helium. Let it go. Helium's gone. Now kind of shake it all about. Okay, good. Now air is in there. Okay, now we're going to go back to a heavier gas. Now notice the balloon valve here is pointed downward because this gas is heavier than air, so it's going to fill the container the other way. Now this is argon. So this is heavier than air. So we're going to flush out the air. We got to keep the flask this way because if we don't, the gas will be argon. Okay? Sorry. That's aggressive enough. Keep the flask upright, and now put the top on nice and tight, and then we're going to mass this guy out. Okay? All right. And let's see what you get over here. And I'm just going to get around student L.
What?
Oh yeah, let it zero out first.
Did I turn off?
You're aggressive. Yep, I think you might have.
Yeah.
Okay. Did you zero it out first?
Yeah.
Okay. Let's make sure. Make sure it goes to zero first. Okay, good enough. Good job. So now you got 93.025. Again, subtract out the mass of your empty evacuated container from that. Now you have the grams of gas B, which is argon. To get the grams of each gas, A and B, you had to get your empty evacuated flask. So whatever the flask is with the air, you subtract out the mass of the air using the density just to get your empty flask. So those two measurements with the gases, one inverted, one upside down, subtract out the evacuated flask from that, and it's not going to be big. Gases are tiny particles that take up a lot of space, so you're going to have a low number of grams. Use your R. Temperature has to be in Kelvin. volumes in liters, so everything cancels off. And of course, our pressures in atmospheres, so everything should cancel, okay, to give you grams per mole. Molecular mass is grams per mole, okay? So if you notice, this is going to be grams. This is going to be atmosphere liters, mole kelvins. This is going to be a temperature in Kelvin. This is going to be volume in atmospheres. I'm sorry, pressure in atmospheres, volume in liters. And so everything cancels except grams over moles. And that's the lab.